We continue with section 7.3, invariant subspaces of real vector spaces. So to recap the previous section, first of all, if V is a finite dimensional vector space over an algebraically closed scalar field, so this is important, then we know for sure each linear operator on V has an eigenvalue in F, and then we also saw that if we denote this eigenvalue with lambda, then the null space of this operator T minus lambda I is actually T invariant. This was theorem 7.2.1. Then we have the problem that R is not algebraically closed, the set of real numbers, or the field of real numbers. So that means that theorem 7.2.1 doesn't apply, and more importantly, we even have example with A equals to, for example, 0, 1, minus 1, 0 matrix, and then the determinant of A minus lambda I equals to the determinant of minus lambda 1 minus 1 minus lambda, which equals to lambda squared plus 1. And if we want to solve this characteristic equation for lambda, when we set this equal to 0, the characteristic polynomial, we get that lambda equals to plus or minus I, which are not elements of the real numbers. That means there is no real eigenvalue, and also there is no A invariant subspace of dimension 1. Of course, R square is, although trivial, but it is two-dimensional A invariant subspace. So this is trivial because it's a subspace in R2, but it's actually equals to the whole vector space. Maybe a better example is to have a 4x4 matrix, although this is large. We will see why we're not going to consider 3x3 matrices in the next theorem. But as an example, let's look at a 4x4 matrix with these entries. To calculate the eigenvalues, we have to look at the determinant of A minus lambda I. Of course, you are welcome to use MATLAB, but this can be still done without MATLAB. So we subtract lambda from the diagonals. This is a lot of simple calculations with a lot of places to make mistakes. So subtract lambda from the diagonals, and then good place to start is with the first row to evaluate. We have 2 0 entries. That makes it a little bit easier to evaluate the determinant. So it's 6 minus lambda times the 3x3 matrix that we obtain by covering the first column and the first row. Then minus 10, the second entry. Then the determinant of the 3x3 matrix that we get by covering the first row and the second column. Expanding this 3x3 determinant is again nice because it has a lot of zeros in the first row, for example. So if we expand it using the first row, we get minus 16 minus y, minus 16 minus lambda, times the submatrix subdeterminant, which is just 2 by 2 now, and the rest is 0 when we use these next two zeros. Then this part is similarly easy using the first row, because only the first entry in the first row is not 0. So we get 26 times the 2 by 2 determinant. Then it's nice to notice that these 2 by 2 determinants are the same actually. And that means that we can factor this out. Also, this is the product of the, if I rewrite this as minus lambda plus 16 times minus lambda minus 16, then this is the sum and the difference of the same two quantities multiplied together. So we have the identity for this, that this is the difference of the squares. Minus lambda square is just lambda square, and the minus 16 square. Then after factoring out the 2 by 2 determinants, we also have plus 10 by 26, which is 260. And these 2 by 2 determinants, after factoring them out, this is minus 9 minus lambda times 9 minus lambda minus minus 6 times 16. So 16 square is 256. So this is lambda square minus 256 plus 260. And here there is a similar identity, but instead of 16 we have 9. So we're going to have lambda square minus 9 square, which is 81, and then plus 96. What we get is lambda square plus 4 and lambda square plus 15 as multipliers. So this is the characteristic polynomial. And actually the important trick here is not to multiply this out, because then it will be hard to factor it out in order to solve when we set this equal to 0. So setting this equal to 0, we see that the way you can get 0 is that one of the factors is 0. Lambda square plus 4 is 0. You get plus minus 2i as a eigenvalue, and the other two eigenvalues from lambda square plus 15 equals 0 is I times plus minus square root of 15. So these are complex eigenvalues, which means that, again, A has no one-dimensional invariant subspace. And A is acting on the R4 vector space, since this is a 4 by 4 matrix. So the idea is that if the eigenvalues are not real, then we don't have one-dimensional invariant subspaces in the corresponding vector space over the real field. It turns out that although we don't have one-dimensional subspace, we have two-dimensional in this case that are invariant. This is the next theorem that says every operator on a finite dimensional non-zero and real vector space has an invariant subspace of dimension 1 or 2. We have seen dimension 1 before, and also we saw cases where we didn't have dimension 1, and it turns out that if we don't have dimension 1, then we will have dimension 2 invariant subspaces. In fact, in the very first example, we already saw that, but that was a trivial example because the whole space was two-dimensional. It will be interesting to see how, in this 4 by 4 case, we can have a two-dimensional invariant subspace. But first, let's see the proof of this theorem. Suppose we have V real vector space, and that the dimension of V is denoted by n, and that is equal to 1 or larger. And let T be a linear operator on V. Then we choose a V vector from this vector space such that v is not 0. Then similarly, as we did in the previous section, we consider the list starting with v, then tv, and so on, larger and larger powers of t, like up to t to the nv. So this list has n plus 1 vectors in the n-dimensional space v. And we know from before that that means this must be linearly dependent. So by the definition of linear dependence, that means there exists a0, a1, an scalars. By the way, it's supposed to be the real numbers, such that we get the 0 vector as a linear combination of these vectors, a0v plus a1t v plus a2t square v all the way up to an t to the nv. This can be also written as using the sigma notation, I going from 0 to n, and then we have ai using the notation t0, which is just the identity operator. Then we can use the notation t to the I times v. So then we can define an associated polynomial p of x, which is the same sum, the same coefficients, and then the ith power of the operator is replaced with the ith power of the variable x. So here the fact that R is not algebraically closed, but the complex variables are, or the set of complex variables is, means that this polynomial could be factored into linear factors in the complex numbers, but not in the set of real numbers. So what this means is that in the real numbers, we cannot factor it completely. So what we can do in the real numbers is we can write with the leading coefficient is an, and then we can have some linear factors for sure. These would be the eigenvalues, x minus lambda 1, x minus lambda r, or at least some of them supposed to be the eigenvalues. So these correspond to real roots. And then the ones that cannot be factored in the real numbers, but they can be in the complex numbers, they become quadratic polynomials like x squared plus alpha 1 x plus beta 1, and the last one perhaps x squared plus alpha k x plus beta k. So these correspond to complex roots, and all the, well, an we already know that real number, but then also these lambdas are real, alphas are real, and the betas are real, and altogether we have the number of real roots r plus the number of complex roots, which is then k, larger than or equal to 1. And if these quadratic polynomials are irreducible, not factorable in the real numbers, that means actually that the discriminant, as we have seen in college algebra, the discriminant is alpha j squared minus 4 beta j, should be negative. So then what we have is that we have the 0 vector if we substitute into this polynomial the operator t, and then we apply it to v. And in the factored form, this becomes an t minus lambda 1 t minus lambda r, and then the quadratic part t squared plus alpha 1t plus beta 1 and t squared plus alpha k t plus beta k applied to the vector v. So what we have here is that if this equals to the 0 vector again, and since v was not 0, what we have here is that we apply these mappings one after the other. This is actually a composite map. We start usually from the right, so we apply to v this operator, then whatever we get here, we apply that operator. So starting with a non-zero vector, applying the mapping, first of all, it's t squared plus alpha k plus alpha k t plus beta k. Then we get a new vector. Then we apply the next one and the next one. So we get new vector, new vector, new vector. And then suddenly, somehow, it's supposed to be equal to the, at the end, equal to the 0 vector. So at some point, maybe not the very last one, but at some point we reach the 0 vector with these mappings. And clearly, starting with the 0 vector, since everything is a combination of linear parts, well, this t square is actually two linear maps applied one after the other, so that's also linear. Everything is linear. So this is also mapped to the 0 vector under this p of t operator, which again, this is linear. So what this shows is that this p of t operator is not injective. So if this is not injective and this is a combination of these factors, then we have two options. Either one of the t minus lambdas is not injective. So let me write t minus lambda j I is not injective for some j going from 1 to r, or one of the quadratic ones. So that means t squared minus alpha k t plus beta k. Now here I omitted the identity operator, but that's what it means to add a constant beta k. So it's possible that this is not injective, or actually one of them. So let me use the index j is not injective for some of the j's going from 1 to k. So in the first case, if t minus lambda ji is not injective, then what we saw in the previous section is that then we have a one-dimensional t-invariant subspace. And that's actually the null space of t minus lambda ji. It's a one-dimensional t-invariant subspace. Then if we have the other case, if t squared minus alpha j t plus beta j t in beta j I is not injective, that means that for some w vector which is not 0, we get that t squared w minus alpha j t w plus beta j w equals to the 0 vector. That's what being non-injective means. And then it turns out that from this equation, the subspace, let me denote it with w, the span of this w vector and tw vector is t-invariant. To see that, what we have to show is that for any vector in this space, when we apply t to it, we remain in this space. Yeah? So that means that in the span, we have vectors like linear combinations of these two vectors elements. So that means for arbitrary c1, c2 real numbers, when we look at the linear combination of these two spanning elements, C1W plus C2TW, and then we apply T to it. Using the linearity, we get C1TW plus C2T squared W. So C1TW is already in W space, and for C2T squared W, what we can do is we can solve this for T squared W. And what we get is that this is C1TW plus C2 times, rearranging this, made a small mistake, this was supposed to be plus. Yeah, and this was supposed to be plus, although it doesn't really matter, the notation. The point is that it's irreducible. Substituting when we solve for T squared W, we get minus alpha J TW minus beta J W. And then we can collect together like terms. So TW collected together, we get that this is C1 minus C2 alpha J TW, and the other term is minus C2 beta J W, which is another linear combination of these two vectors, W and TW. So that means this is also in the span of the two vectors. So we get this T-invariant subspace W. Now the question is whether it's one-dimensional or two-dimensional. This suggests that it's two-dimensional because you have two spanning elements. So we have two cases. If this turns out to be one-dimensional, then that means that these are linearly dependent. So that means that TW could be written as a scalar multiple of the other vector, but that would mean actually linear factor, which means that T minus lambda I W equals to the zero vector. And that's a contradiction because we obtain this from an irreducible factor. Hence, we get that W has dimension 2, and it is T-invariant subspace. So this completes the proof. We obtained a nice two-dimensional T-invariant subspace. So returning to the example, we had again a 4x4 matrix. That means this is a linear operator on the real vector space R4. It was given by the 4x4 matrix 16 minus 10, 0, 0, 26 minus 16, 0, 0, minus 6, 0, minus 9, minus 6, minus 7, 10, 16, and 9. And we obtained the eigenvalues as plus minus 2i and plus minus I times square root of 15. Complex eigenvector values. That means we don't have one-dimensional invariant subspaces. So let's see about two-dimensional ones. According to the previous theorem, we obtain this from the quadratic factors in the characteristic polynomial. One of them supposed to be not injective. So the quadratic factors that gave us the eigenvector values were lambda square plus 4 and lambda square plus 15. So that means that if we substitute the matrix and we apply to a vector v, we should be able to solve it, one of them, for the homogeneous equation. So let's start first with, well, first of all, we have to calculate P of A, which is a squared plus 4. Well, we need one of the factors, so it's either a squared plus 4 that gives the 0 vector, non-injective, or the a squared plus 15. In both cases need the a square. So that takes some time to calculate. And again, you have to make sure you are not making mistake. Maybe MATLAB can be used, at least to double check your answer. So we get minus 4, 0, 0, 0, and 0, minus 4, 4, 0, 0, 0, 0, minus 15, 0, minus 11, 0, 0, minus 15. So I hope we are not at the level where anybody confuses what a square is. A square is not the square element by square of the matrix entries, it's a times a. So we have to do 4 by 4 matrix multiplication of two matrices. What's nice to see here in this a square is that when you add 4 or add 15, a lot of half of the diagonal entries will be 0 in either case. So what the theorem says is that either the null space of a squared plus 4i or the null space of the a squared plus 15i of dimension 2. If you look at a squared plus 4i, and we want to solve this for the homogeneous equation, what we get is adding 4 to the diagonals. We get 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, minus 11, 0, and then minus 11, 0, 0, minus 11, and then the augmented matrix. So from here we immediately see that this row says that x3 should be 0, and the last row says, well, the first two rows says nothing. It's just the trivial 0 equals to 0 equation. And the last row says that x1 plus x4 equals 0 if you divide through with minus 11, which means that x1 is minus x4. So from here we get the solution for x1, x2, x3, x4 solution vector. We have minus x4 in the first component. X2 is, by the way, arbitrary, so there is nothing about x2, so that means x2 is arbitrary. x3 must be 0, and x4 is just x4. That's again a free variable. x2 was also a free variable. So nice place to practice solving homogeneous equations and writing the solution in parametric form. We get x2 times 0, 1, 0, 0, and plus x4 times minus 1, 0, 0, 1. So that means these two vectors are the basis vectors for the null space of a squared plus 4i. It's the span of these two linearly independent vectors. It's easy to see that these are linearly independent since one has non-zero second entry while the other has 0 second entry. So actually this has dimension 2. Now this doesn't have to be the case, but we can check whether the other factor has dimension 2 subspace. Also I should mention here that this is A invariant. By the way, it's also nice to check that this is A invariant, this subspace. So it's enough to check what happens to the basis vectors, writing this in the form of A. So this says that we get, by this 1 in the second component, we pick up the second column of A, which is minus 10, minus 16, 0, and 10. And if we separate this, if we try to see that this is in this span, in this null space, we can separate this as minus 16 times 0, 1, 0, 0, and then plus 10 times 1, 0, 0, 1. And since these are exactly the basis vectors, that means that I made a mistake with the sign, so this should be minus 1. So now these are the basis vectors. So this is in the span, this is in the null space of A squared plus 4i. So it is really A invariant, especially if you also check the second basis vector. So what this says is that minus the first column plus the fourth column of A, that gets picked up. So using the definition of A, this is minus 16, minus 26, then 0, and 16, which can be again separated into a linear combination of the basis vectors. Minus 26 times 0, 1, 0, 0, plus 16 times minus 1, 0, 0, 1. So again, these are linear combinations of the basis vectors, which means that this is again in the null space. So that says that really the null space of this quadratic factor is A invariant. It turns out that the null space of A squared plus 15i is also a two-dimensional A invariant subspace. So what we have is actually that R to the 4 can be written as the null space of A squared plus 4i direct sum with the null space of A squared plus 15i. Which means that if we denote this with W1 and W2, that means that this linear operator A, which is the matrix, mapping from R to R4 to R4, can be written as A restricted to W1 plus A restricted to W2 subspaces. Please note, if you look at the theorem, it says that we have factors that are not injective for some j. It doesn't say that all of them have to be not injective. In this case, in this example, we got that both quadratic factors are not injective, but it doesn't happen all the time. So we cannot always write the whole vector space as a direct sum of null spaces. So we cannot always write the vector space as the direct sum of invariant subspaces. This happens if we have n different roots, then we have linear factors. If all the roots are different, but for example, if we look at an example with repeated real roots, for example, if A is the matrix 1, 1, 0, 1, then the determinant of A minus lambda I is 1 minus lambda 1, 0, 1 minus lambda, and this becomes 1 minus lambda square. So we only have one repeated eigenvalue, lambda equals 1 eigenvalue with multiplicity 2. And if you look at the null space of A minus lambda I, which in this case is just A minus I, that's the null space of 0, 1, 0, 0. So if you want to solve the equation 0, 1, 0, 0, x1, x2 equals 0, 0, we immediately see that these two equations, the first equation says that x2 is 0, and then x1 is arbitrary. So that means that the null space is just the span of one vector, which is 1, 0, since x1 is free. We can take x1 equals to 1 and x2 is 0. So this has dimension 1. This is A invariant, we know that. But the only other A invariant subspaces are the 0 subspace and then the R square itself. So other than this one-dimensional A invariant subspace, we don't have another one that we could use to split up R2. So that means no way to write R square equals W1 plus W2 with A invariant subspaces, at least with non-trivial A invariant subspaces. The only way we could write this is that R square equals to 0 subspace plus the R2 subspace itself, but this is trivial. So finally, the last result in this section is the following theorem. Every linear operator on an odd-dimensional real vector space has an eigenvalue. So the proof of this theorem actually based on this very simple observation that if you have an odd-dimensional real vector space, then the characteristic polynomial has degree which is odd. And then that means that, for example, if you have a cubic polynomial, then as x approaches infinity, it goes to positive infinity. As x approaches negative infinity, it goes to negative infinity. So that means at some point it must cross the x-axis where it has a root. And this root will be an eigenvalue. So this is true no matter what the leading coefficient is and what the odd degree is. Actually, for characteristic polynomials, the leading coefficient is supposed to be 1, since it's based on, or minus 1, by the way, because it's based on the a minus xi. So we are subtracting x and we have odd number of them. So in fact, the true picture is that the limit is negative infinity when x approaches infinity and positive infinity when x approaches negative infinity. Still, this is the case that there must be a root since these are continuous functions. There is a more rigorous proof for this at the very beginning of the class. If you want to see lemma 1.1.2 proves it in a more analytical way than what I did here, waving my hand, that we know from college algebra about the properties of polynomials with odd degree. But the point is that we have a quite complete picture of linear operators now on real vector spaces. So what we have is that if we have odd dimension, then we have for sure a one-dimensional T invariant subspace. If it's an even dimension, then we might not have eigenvalue, which is real. Still, we know that we have either an eigenvalue and then one-dimensional invariant subspace, or if no real eigenvalue, then we have a two-dimensional T invariant subspace. This is not all what we have. Of course, we can have higher dimensional, but at least these are guaranteed that we have these one- and two-dimensional subspaces. So we might have, of course, also higher dimensional T invariant subspaces. This is the last theorem in this section, and with this, we finish this chapter. We skip the rest about commuting linear operators. So commuting linear operators would mean that you can change the order when you combine them together, like S composite T or T composite S. Sometimes we put the composite function notation, sometimes we don't. Usually we don't. So this is a very special property. It has some requirements about the eigenvalues and eigenvectors. Clearly, it doesn't happen very often in real life. We have, as a first examples for matrix multiplication, usually this is covered in undergraduate linear classes, that if you multiply together two matrices, usually they are not equal. And the next chapter we continue with is chapter 8 about inner product spaces.